Alright, so now let's start recording. Alright. Something's working. Yeah. So let's get started. Today we have Dr. Kung Zhang again. He's going to talk about causal structure learning.
Okay, thank you, Kaihan. So this lecture is about how to learn the underlying causal structure or the causal model from observed data points. And actually, we have some classes on causality. Sometimes, in some years, I give classes on causal discovery, and this year, Peter Spertis is giving a class, philosophy of science, but actually it's about causality, it's about the causal search. And Peter Spertis is the one who is the most familiar with a lot of methods for causal discovery, and who has the best understanding of a lot of algorithms for causal discovery. So if you are interested, maybe you can sit in the class, philosophy of science class. Okay, so let's get started. Here you can see a motivating example. Over here, we want to find the causal relation between different things, between wheat, rice, agriculture, and culture, psychological differences within people. So clearly, in this example, you can see we cannot really do intervention. We have to find a way to analyze the data, right? By analyzing the statistical information of the data, we want to draw some conclusion about the underlying causal relations. And this is known as causal discovery. So basically, you analyze observational data, and you want to find the underlying causal structure or the underlying causal model. And first of all, a lot of people think that, oh, it's not possible to discover causal information from observational data, right? They just think that we have to make use of interventions or changes in some way to discover causal information. But if you think of the problem from the purely statistical or purely machine learning perspective, you can do so. Why? Just recall the problem of supervised learning. Suppose you just want to fit a curve here. You are given a couple of data points here, and you want to fit a curve. If you go back 50 years, you can say, oh, you would say, oh, the problem is not well posed, right? I have so many possible solutions. I can fit a line, I can fit a quadratic function, I can fit a very complex function, right? The problem seemed to be ill-posed. However, nowadays we don't say so, right? We know that, oh, if you just give me a lot of data points, I can find the best function, in the sense that the function can make prediction into the future, right? Suppose you give more data points, I can use this curve, this function, to make prediction, right? So now you can see, if you compare our view, current view, with the very old view, it's very different. Now the problem is clearly well-defined, well-posed. How can you solve it? How do we solve the problem? You can see, basically, we made the problem very clear. Now we know, okay, if I want to solve the problem, I have to, first of all, my purpose, my goal should be very clear. Here we want to find a function in a predictive way, because we want to find a curve to make future predictions, right? Then, under some assumptions, basically we have a functional class, and then we can relate the predictive performance to the complexity of the function in some way, right? And then we can perfectly solve the problem. So the tricky part is how we can make use of complexity measures and regularizations so that we can find the best function among all possible solutions, right? This is also the story for causal discovery. At first glance, you may think that, oh, how can I know the underlying causal model? This is something about the physical world. I'm giving only those observed data points, right? But actually, it's the same thing. It's something like induction, right? You are given data points. You want to see something behind the data points. Okay? So that's why we should be very optimistic. It's hard, but it's clearly doable. So actually, you can see different constraints, including structural constraints and regularization techniques, are very useful in causal discovery. Okay, so I'm going to talk about, regarding causal discovery, I'm going to talk about the constraint-based approach. Here, by constraint, I mean conditional independent constraint. And then I'll talk about the classical score-based search. And then I'll talk more recent approaches based on functional causal models. And finally, I will talk about some extensions. And then I will very quickly say a few words about how to do other learning problems, how to solve other learning problems from the causal perspective. So, did you learn Bayesian network learning at all? You know, okay, you know something about it. So, what's the difference between Bayesian network learning and causal discovery? Clearly, they're related because you want to find a graph, right? But sometimes you even want to find a model, not just a graph, including the parameters. So what's the difference between causal discovery and Bayesian network learning? Yeah.
Isn't that causal discovery is more strict than Bayesian network learning?
By strict, what do you mean by strict?
I think in the last lecture we talked about this. Like if you want to do some sort of causal discovery, you need to be able to fix the value of some node in your graph, and while keeping everything else the same, see how this will affect other variables, and using that make some sort of decision about the causal relationship between the two variables.
Good. So what you said is more related to causal inference. So you are given something. You are given, and very often times you are given a causal structure. You want to identify the effect of something on the other thing, right? This is called the causal inference. Usually, I use this term, causal inference, because you want to infer the effect of, say, variable x on variable y, right? That's called, here you want to find the structure, right? And it's more like, what you said is more like randomized experiments, right? I want to fix a lot of other variables, relevant variables, and then I change something, right? And finally, I can see whether this change over here will lead to some change in the target variable. This is called a randomized experiment, right? Here, the problem is, yes, you can do so. But if you want to discover causal model this way, I would say it's not complete. Why? Because you can see, oh, this one, x changed y, influenced y. But very often times, you don't have the model. You don't know how exactly x changes y. You don't have the functional model. This is one thing. Okay, and furthermore, you make use of interventional data. You have to do interventions or randomized experiments, right? That's so hard, right? Yeah, let's talk about problems in, say, social sciences. Suppose we want to see the relationship between, say, divorce and something else. You cannot force people to divorce, right? So that's why in social science and in most disciplines, it's really very expensive or even impossible to do interventions, to have interventional data. Okay, so here we want to see, we really want to see everything by analyzing observational data. You are giving a single data set. That's all. Okay, so in Bayesian network learning, you also have a data set, right? You want to make use of the statistical properties of the data, and you want to finally you will end up with a Bayesian network. So what's the difference? They are very similar. Let me give you an example. Suppose you just have two variables, x, y. If you use Bayesian network learning, what will you get? You can get x from x to y, the edge, or from y to x, right? You don't care. As long as you capture the same independent relations, right? Or statistical properties of the data, it's fine. But if you talk about the causal model, they are so different. You really have to distinguish between the two things, x to y and y to x, right? Because they have totally different causal meanings, causal interpretations, right? That's why if you can really determine the direction, you'll be happy, right? That's good. If you cannot, not a big issue. Why? I just say, I don't know. Later you can see how we can deal with the problem. You just say, oh, I don't know. It's equivalent class. Maybe you want to determine the direction by making use of background information or some other type of information. But here, based on the data, I have no idea. I can only give you a set of decks. Okay, so causal discovery is really about how to discover causal information from data. Okay, and clearly, if you have a method for learning Bayesian networks, usually, right, you can use it for causal learning. How? I can first learn a Bayesian network. I suppose the model assumption really holds, right? If I assume it's linear, right? Basically, the data should be linear. Otherwise, the result, the learned network could be totally wrong. So then you have to do some transformation. Why? Because I know that not all directions or orientations over there are trustable, right? They are just Bayesian networks. It's not necessary to have causal meaning. That's why I should be careful. Actually, there exists some method to convert Bayesian networks to the so-called equivalent classes. So by making use of the equivalent classes, you can really include all the directional information in the solution. And in some situations, we can fully identify the underlying causal structure. You will see why later. Okay, so you already talked about those Markov condition, right? So let me skip this part. Markov condition, local Markov condition not enough. Why? Because we want to see whether variables are conditionally independent given an arbitrary set of variables. And it's D-separation. What D mean? D is directional. It's not dependent, D is directional. Why? Because when we determine whether two variables or two sets of variables are D-separated by another set of variables, we have to make use of a direction. That's why it's called directional separation. Okay, with no D-separation, then you can just do some exercise. Let me skip this. The intuition, yeah, you can just basically, if you have this picture, you can easily understand why we can benefit from the definition of D-separation. Local global Markov condition. Okay, let me skip this. They are equivalent of X. Causal sufficiency, this means every time you are given a set of variables, say V, right? If the direct common cause of two variables, say X, Y, is also in the given set of variables, we say it's causally sufficient. In other words, there's no missing or hidden direct common cause of any two given variables. This is sufficient. Of course, in most situations, we have hidden variables as causes of single variables, right? So I have a cause of X, which is not recorded. Then this is not a common cause. It's totally fine. We say this is a part of the noise term, right? And here, the common cause is horrible. You have to deal with the common cause. And common cause could make a lot of things very complicated. So I said, when I define the confounder, I said it's a direct common cause of two variables. Why did I use direct? Because you can see in some textbooks, they just say a common cause of two variables. Here we say it's direct common cause of two variables. Why? Because over here, suppose you have Z going this way. Forget about this guy. Now you can see Z is the common cause of both X and Y. Z is the direct cause of X and indirect cause of Y, right? So you can still see, oh, Z is the common cause. But this is not rigorous. So we have to say it's a direct common cause of two variables, then it's the confounder. Here, by assuming causal sufficiency, basically you just get rid of this possibility. We'll be happy. Is that clear, right?
Is this the definition of the...
Yeah, definition of causal sufficiency, yeah. So this structure, this is very important. Sometimes we say this is an unshielded collider. I want to use this structure because to me it's clearer, it's very intuitive. We say this is the V structure. Here you can see the two variables, I say X, Y. X and Y are not adjacent. X, Z adjacent, Y, Z adjacent. And X and Y are causes of Z, right? This is the V structure. This is very useful. Why? Because here you can clearly, suppose you are given three variables. And if you assume causal sufficiency, then you can see, you can easily determine this structure from conditional independent relations in the data. So here in this case, you can see X and Y will be independent, and X and Z will be always dependent, y and z will always be dependent, and xy will be not just independent, but also conditionally dependent given z. Right? So whenever you have three variables whose conditionally independent relations look like this, you are pretty sure that, oh, it's very simple. X and y not adjacent. X and y are basically causes of z. This is the V structure. Okay? So I already assumed something when I tried to go from statistical independent relations to the graph. Later you will see what assumption I already made. Okay, this is V structure and Markov condition. You can see a lot of relations. And we can easily see conditional independent relations from DEX by making use of either Markov condition or deseparation, right? Or global Markov condition. Basically, if two variables are deseparated by another set of random variables, we know the two variables are conditionally independent given that, right? So it's very easy, very good. However, now we want to go in the reverse direction, right? We want to go from independence relations to the causal structure. What can we do? So far, we have no idea, right? So here you can see if they are deseparated, this is the property of the graph. Then, according to the Markov condition, local or global Markov condition, we know that x and y are conditionally independent given z. This is very clear. But if you want to recover the information from the graph, what can you do? We know that a fully connected graph is not really informative. We really want to have a sparse graph, right? What can you do? So you can see the counterpositive of this claim is that if x and y are conditionally dependent, then they are adjacent. Then they are not deseparated, right? They are not deseparated. This means I can derive a lot of relations in the graph, a lot of relations between pairs of variables which are not deseparated, right? However, I want to determine whether variables are actually deseparated. If they are deseparated, you can see the following thing. If two variables are deseparated by anything, then we know that the two variables are not adjacent. Right? Do you know why? Because if they are not adjacent, you can always find some set of random variables given which they are deseparated. Right? So they are adjacent if and only if they are always deconnected. They are not deseparated. So you want to go from independence. You want to go from independence to deseparation. That's the problem. Clearly, without further assumptions, we cannot do so. If you just apply Markov condition, you can see you can always end up with a fully connected graph, because clearly Markov condition will always trivially hold. No variables are deseparated. That's why I cannot see any conditional independent relation in the data, right? If you see something by accident, you can see a lot of things, right? So what assumption should we make?
So
yeah.
Just one question about the previous slide. So the goal is to go from a set of conditional independence to the graph.
Yeah.
So assuming that I can get the IMAP, I can somehow construct the IMAP, I can retrieve the graph.
Yeah.
From computational point of view, the IMAP may have like so many elements in it.
Yeah.
And so what can you say a few words about naive, at least naive sense, like if I want to fill in the IMAP by searching, how the computational cost would be?
This really depends on the procedure. So later you can see first, I think the first algorithm was called SGS, Peter Spertis, Clark Glimmer, Richard Shines. So SGS, that is the first letters of their last names. That method, the computation is very expensive, right? You have to check all conditional independent dependent relations. But the PC method, I will talk about it later, is relatively efficient because of some tricks. You don't do all conditional independent tests. You can make use of what you have to reduce the number, basically to reduce the number of tests you have to do. It's very efficient. And there are some variations of this procedure. That's why it really depends on the search procedure.
So when you say conditional independence test, this is again observational data, right?
Exactly.
It cannot truly reflect the correlation between that.
Say again?
So the observational data may not truly, you can only model the covariance and that may not truly be representative of the correlation. So
what can you infer from the data?
So is there like a way of like coming up with more robust ways of establishing dependence between variables?
That's what we want to do, right? We just analyze the independence and dependent relations, statistical properties of the data, because we want to end up with a causal graph.
I guess
Yeah.
what he's trying to say is that your data is still going to be observational. Biases and are going to be in there regardless of what you do, right? So how do we know that, given that set of data that might have biases, and that the data might not represent some distribution efficiently or whatnot? How do we?
Then basically now you can see you have practical issues. This is right. This is not the first thing you should think about to solve the problem. You always have a lot of practical issues, right? You always have to make use of suitable assumptions. First, you can see when we use PC, we assume it's causally sufficient. We assume there are no selection bias, and so on. And later, you can see how people could deal with confounders and selection bias and nonlinearity and so on. Okay, that's how we can solve the problem. If you have a new problem, you have to solve the problem this way, right? That's a very good one. Okay. So let me give an example first. Here you can see health condition. We have 3 variables here: health condition, healthy lifestyle, risk, and mortality. So you can see intuitively, suppose this causal structure is true, is a true one. Health condition should be dependent on risk of mortality because of the causal relations, right? There's the causal influence from here to here. That's very good. But by accident, or for some reason, it's possible to see that they are independent. They are almost independent, especially if A equals minus BC. The causal influences in the two, basically, the two pathways will cancel out, right? If A equals minus BC, you will see that X, Y, the same thing will be here. X and Y are independent. This is horrible, right? Although X influences Y, they are independent. This is called violation of faithfulness. When we assume faithfulness, basically, we say that this will not happen. In other words, when we assume faithfulness, we make the following statement. If, like, give it somewhere, it says the following thing. If you have an independent or conditional independent relation in the data, then you can see the independence relation from the graph. It's implied by the Markov condition on the graph. That means if you cannot see this independent relation by applying Causal Markov condition to the graph, then it should not be there. Okay? This means if you follow faithfulness assumption, then here, this guy X and Y should not be independent. And there are so many ways to justify why we can assume faithfulness. One way to justify this is based on modularity. Remember last time I talked about modularity. If you have a causal process, basically here, the generating process for this guy and the generating process for this guy will be completely separable or independent, not relevant at all. Then you can see faithfulness is violated when you have coupled parameters. The parameters are just coupled, right, in some way, so that the influence of X on Y is exactly 0, right? So you can see if all those parameters were chosen independently, the chance of having violation of faithfulness is 0. It's very low, right? The measure would be 0. So this is the faithfulness assumption. Basically, now you can see the following thing.
So can I ask something about faithfulness? So is the faith? So we know that when we have a graph structure, that specifies the family of the distribution, but we can always play with the parameter to introduce fake independence. So the faithfulness is saying that
there's no fake.
Yes, there's no fake.
No fake independent relation in the data.
We always say that IMAP of the graph is, and we have IMAP of a probability and
the same.
IMAP of the graph, and they are the same.
The same. Exactly. I didn't use that term. Yeah, they're the same. But you can see here we assume faithfulness, but modern approaches to causal discovery already avoid this assumption. We don't assume faithfulness anymore. Later you will see this. However, if you want to use conditional independence-based method, you have to assume something like faithfulness. Because over here, we really make use of very little information. To get something very strong, you have to make additional assumptions. Okay, with Markov condition, we can go from the causal structure to the property of the data, especially statistical properties of the data, including independence, basics, just independent relations. And with faithfulness assumption, now you can see we can go back. It says that all observed conditional independent relations in the data are just entailed by Markov condition on the underlying graph. That means if you see something, independent relation, then clearly this is something, some property about the graph. Y and Z are disseparated by something, right? Otherwise, if you apply Markov condition, you cannot see that Y and Z are conditionally independent given X, right? So with Markov condition, we go from graph to the property of the data, statistical properties of the data. Further, with faithfulness assumption, we can go back. That means we can do causal discovery because we have the correspondence between missing edge and independent relation over here, right? In the data, we have independent relation. Over there, we know, oh, there are no edge between the two variables. So now we already got the basic idea. How can we solve the problem? So first, can we find the skeleton of the causal structure? I think you already have the answer, right? You know whether we can find the skeleton of the causal graph. Why? Because we know if two variables are not adjacent, say it.
Then there will be conditioning variables.
Yeah, exactly. Thank you. So clearly you can find a set of random variables conditioned on which they are independent. That's very good. Because we make use of two assumptions called Markov condition and the faithfulness assumption of the model. And then what's the difference? Here I use a skeleton. Did you talk about the Markov network learning? Right? How to learn undirected graphs?
No.
Not at all. Okay. So in statistics, you can see a lot of people talk about how to learn Markov networks or conditional independent graph, right? They use the inverse covariance matrix or precision matrix, right? You can also end up with the undirected graph. Here, this skeleton is different from that undirected graph. Why? Let me give an example. Suppose we have x, y are independent, they are not adjacent, and they are causes of z. In this case, you can see the learned Markov network will be fully connected. You will also have this. But if you learn the skeleton of the causal graph, you will end up with this. Right? We are not going to have, ideally, we are not going to have the connection, the edge between x and y. Because Markov network is defined this way. If two variables are conditionally independent given the rest of the variables, all the other variables, then they are not adjacent. In this case, you can see x and y. Although x and y are independent, they are dependent given z. Because z is the common effect, right? X and y are dependent given z. That's why in the learned Markov network, they will be adjacent. This is very different from what we want to find, right? We want to find a causal graph. We don't want to have that kind of purely statistical relationship between variables. Also, we also make use of independent. We really want to say something about the underlying physical, ontological causal picture. Okay, so we can find the skeleton. That's very good. Can we determine the causal direction? Now you can see, at least in this case, if you have a V structure, you can. Why? Because if the direction goes in any other way, you are going to end up with a completely different set of independent relations. So here, for V structure, right, we know x, y independent, or I can give, do I have another example? Let me give you another example. Here, W is the common cause of x and y, and x and y are causes of z. You can see x and y independent given W. X and y will be dependent, conditioned on any set of variables that contains z, because z is a collider, z is a common effect. And that's it. So here, if I have the skeleton, then I know the direction between x and z and between y and z. Why? Because if the direction goes this way, now you can see, oh, x and y will be conditionally independent given w and z, right? This is totally different from what I get. Okay, originally x, y independent given only w, right? Cannot, basically condition set cannot include z. But if I change the direction this way or this way, basically x and y are independent given w and z. Okay, that's why we can determine the V structure. Now you can first see an example.
Where did W come from?
Oh, W is just another variable. I just make up one.
I'm not sure I understood like how.
So we have now, in this example, we have 4 variables. In this example, we just have 3 variables.
Let's say we have 3 variables, x, y, z, right? And
Yeah.
we've determined that z, x, and y are not adjacent, so that means that z is in between them somehow.
Oh, yeah, you can say, okay, what
Because
if
we
you
said
have
that
this?
If they're not adjacent, then that means that there's something in between, right?
Yeah.
So that means that z is in between. Which
When you say
means-
there's something between, in this example, yeah, we have something between. We have W, right? W is the 4th variable. And in the first example, yes, we have something between. If the causal directions go this way, we have empty set in between. Because x and y are conditionally independent given the empty set. They are marginally independent. In this example,
But
right?
for example, if the direction of ours was x to z to y,
Yeah.
and z was observed, then x and y would be.
Now everything is observed. All variables I wrote down are observable. So x, now we have causal chain from x to z and from z to y. And then over here you can see x and y will be conditionally independent given z.
Exactly. Yeah. So that
Right.
means that this is a skeleton that this is a causal direction that also works.
Regarding skeleton, right? You are talking about the skeleton, but now we are talking about the second step. After you find the skeleton, can you determine the direction of the causal edge?
Yes, and I'm saying that this is a direction that works, and also this one would be a direction that would work.
Yeah, that's the difference is as follows. If you have this underlying causal structure, x and y will be dependent, and x and y will be independent given z. Right? Over here, you have x, y dependent, x, y independent given z. Right? And over here, if you have, okay, if you have this one, now this is already very messy, forget about this one. If you have this x, y as causes of z, then you are going to have this set of independent x and y are independent given empty set.
Yes.
And x and y will be dependent given z.
Correct.
Now, just compare the two sets of independent relations. They are completely different. You can discover conditional independent relations from data. That means you can determine which one should be the case. If this is the case, you know, oh, this is the V structure. But if this is the case, you have no idea about the direction. Why? Because here, I can also have this graph. You are going to have the same set of independent relations. Let you see this. Yeah. Okay. Okay. So that's clear, right?
Yeah.
Okay. So you can see the example. Suppose I have this causal graph, underlying causal graph, to generate the data. Suppose I have enough data. And then how can we find the causal structure? First, we can find the skeleton by making use of independent relations. Why? Because whenever I see two variables are independent, conditional on anything, I know there are no edge between them. So here I start with a flip kinetic graph. I see independent between 1 and 2. Then I can throw away the edge between x1 and x2, and so on. And then because x1 and x4 are independent given x3, I can throw that edge away. And finally, we can have the skeleton. over here. And then we can find the weight structure. Here, 1, 2, 3 form a weight structure. Because 1 and 2 independent, they are conditionally dependent given 3. Okay? Then we can determine weight structure. And here, you can even determine the direction between x3 and x4. Why?
Otherwise, you create B structure.
Who said that? Yeah, otherwise,
You create B structure.
exactly. Otherwise, you are going to have fake weight structure. Very good. So here, otherwise, if you go this way, you can see, oh, 1, 3, and 4 will form another weight structure, which is fake. You have to avoid that. Okay? So this is how basically the procedure works. You have data. Oh, it's not aligned. You have data, and then from data, you can discover a set of conditionally independent relations as constraints. Then you want to find a DAG or set of DAGs to satisfy those conditional independent constraints. That's it. Here you can see because they are independent with this way, and then we get rid of that, and finally, yeah, we can do this. Here you can see the detail. Basically, we want to go from independent relations or independent constraints to the candidate causal structures. And we made 2 assumptions, causal Markov condition and faithfulness assumption. Some people also say causal Markov assumption. So it's the same thing, but they have different views. When we say causal Markov condition, most of the time we take it for granted, right? And some people actually have different views. They don't think causal Markov condition trivially holds. They want to find an example where causal Markov condition does not hold. Actually, sometimes they raise some examples in quantum physics. Okay, and a typical method is called PC algorithm. P is for Peter, Socrates, C is for Clark Glimmer. The first letters of the first names, Peter and Clark. And so there are 2 steps. The first step is to find a skeleton by making use of conditional independence in a tricky way. In this way, you can see we can do a minimal number of independent tests. And the second step is to do orientation propagation. First, you determine the weight structure, and then you do orientation propagation. I will give you more detail later. And you end up with the Markov equivalent class. Usually, the solution is not unique. If you have a weight structure, the solution is unique. You end up with a DAG. But usually, you have a set of DAGs or equivalence classes. Here, by Markov equivalent class, I mean all those DAGs in the class will have the same conditional independent relations. Okay? Or they are equivalent if you apply the causal Markov condition. They have the same set of independent relations. Okay, we can represent this with a so-called pattern. Pattern basically is looks like a chain graph, but actually some edges are directed and some edges are not directed. Basically, if all DAGs in the solution have the same orientation for the same edge, then you have the edge in the solution. Otherwise, you just use the undirected edge.
So can I ask a question about
Yeah.
step 1?
Yeah.
You say that step 1, x and y are adjacent if and only if there are dependent conditions on every subset of the remaining values.
Exactly.
So if I have n variables, I have to test 2 to the power of n.
Yeah.
So wouldn't that step number 1 non-polynomial?
Okay. The problem is the fellow. If you have a look at PC algorithm, you can see we start from the unconditional independent test, and then you increase the cardinality of the conditioning set. Why? Because if x, y are independent, first of all, this is the proof. Basically, this was proven by, this was given, this theorem was proven by Peter in the later 1980s. And in practice, you can find this phenomenon. If x and y are conditionally independent given something, then if they are deseparated, then they must be conditionally independent given either a subset of the parents of x or the subset, a subset of all variables that are adjacent to x or a subset of all variables that are adjacent to y. That's enough. You don't need to consider every possible combination of the other variables.
Wouldn't you at the beginning, you said you started with a fully connected graph?
Yes.
And if you start with fully connected graph, everybody is there.
But first, you can see first you do unconditional independent test. right? You can get rid of a lot of edges. Since the cardinality of the condition set is basically very low, the power of the test is high. So you start with this test, and then you increase the cardinality of the condition set. Right? Now you condition on a single variable. When you condition on a single variable, you only consider all those variables that are adjacent to either x or y. You really, right? You have a much smaller number of variables to condition on, right? And so on. So finally, the step will. Finally, you can see, oh, you just consider all possibilities, and this step will terminate because you cannot condition on any further variables. Okay, that's why it's very tricky. You can see, otherwise it's really kind of exponential, right? Now it's not. Actually, this is polynomial. If depending on the degree of the graph, sparsity of graph, usually this is just a polynomial in the number of variables.
So where is the catch? Because we know there's no free lunch theory.
Here, because of trick, right? If they are originally, you have to condition on every subset of the remaining variables.
Right.
That's horrible. Now you just condition on all variables, a subset of variables that are adjacent to either x or y. Yeah.
So I guess my question is that at the beginning you start with pairwise non-conditional independent tests, and then you prune the tree, and after that your algorithm is polynomial, but you have to be missing something somewhere. So there should be some theorem that says that we have a polynomial algorithm that recovers a subset of the graph that are within this physical set. Like, otherwise, you have solved it. But non-polynomial.
This is because the trick is that you already assumed something about the graph. If the graph is fully connected, then clearly it's polynomial. It's exponential, right? Because every time you have to do the original thing, you have to condition on every possible subset of the remaining variables. Yeah.
I think the bound that is derived here is based on the maximum degree.
Yes.
So you have a maximum degree bound on the graph that is polynomial based on that.
You have to assume there's a kind of sparsity of thing about the graph. Otherwise, you can trivially think of a lot of examples where this is exponential. And as you can see from this example, yes. So first I consider unconditional independent test, and then I can end up with this one, and then I don't need to go. So here, and then once you arrive here, you will stop, right? And in total, you can see not very many conditional independent tests are needed to find a solution. Okay. Okay. In case you want to see the detail, basically, you already saw how it works. You start with the conditional independent test, and then you increase the cardinality, and finally, you can see, oh, I should stop. And then you find the V structure. It's very easy. Why? First of all, two variables are adjacent. Two variables not adjacent, and they are adjacent to another variable. This is a candidate of this structure. Then you see whether x, z are independent given a subset that contains y or not. If the condition set contains y, we know it's not this structure. Otherwise, the this structure. Okay. Given this structure, you can do orientation propagation. What do I mean by that? So here, suppose you have this. You have x, y, z. Suppose after the this structure, after this structure, no. I see. So here, after detecting all this structure, I have this, then I have to orient this edge this way. Why? Otherwise, you are going to have, if they go this way, then this is going to be a V structure. You know it's not, because you already detected all V structures. And over here, if you go this way, then this edge has to go this way. Why? Because otherwise you are going to have a cycle. Here, in this part, we will assume there's no cycle in the graph. It's a dead. Later, you can relax this assumption. Okay, so this is the first example. You can see this is a classical example. You have a coordinate plane. They want to see something about causal relations between those variables, including sex or gender, IQ, coordinate planes, parental encouragement, and the socioeconomic status of the family. And after doing conditional independent test, basically, you recover the skeleton of this graph, and then finally, this one was derived based on some background information. We know SES cannot be an effect of what? Of IQ. Okay. In fact, in this example, apart from this edge, you can determine the direction, the orientation for all the remaining edges. Can you see why? First of all, can you see why we can determine the direction of this edge? We can determine the direction of this edge between SES and the PE. Why? Because here we have a V structure. See, SES, PE, sex. This is a V structure. That's why we can determine the directions of those edges, right? The same thing happens here. You can determine this edge. So how can you determine the direction of this edge from PE to CP? From PE to CP? Yeah.
V structure between SES and CP?
V structure between SES and CP? You mean this one? You have a third variable, right? Because it's V structure. Which one is the third variable? You mean PE?
Yeah, you can test.
This is not a V structure, right? Because they are adjacent. Each pair of the variables is adjacent. For V structure, right? We have X, Y, Z, X and Y cannot be adjacent, right? Remember the first rule. If you have this, then you can orient this one this way. Why? Otherwise, you are going to have a fake V structure. You can just apply here. I know this, I don't know this, then this one must go this way. Otherwise, if it goes this way, then sex, CP, and PE will be a V structure. That's fake. Okay, so you can see we can really see a lot of information, underlying causal information, by analyzing data this way. And this is the second example. My colleague collected 250 skeletons in the world. He's an archaeologist. And they really want to understand those causal relations. And here we just apply the method PC combined with our kernel-based conditional independent test. And finally, you can see this is the output. So it makes sense. And there are some well-studied phenomena. So here, I think I talked about this last time. And also we have new information because we can distinguish between direct causal influence from indirect causal influence. Here, a lot of papers talk about the influence of diet on cranial shape differentiation. Basically, diet, what you eat, will influence the shape here. Yeah. And a lot of papers talk about this, but here we know, oh, yes, there's a causal influence. However, it's not direct. This causal influence takes place via two other variables: level of attrition in teeth and some other behavior. So you can see by analyzing data, you can really have a detailed understanding of the underlying causal process. Okay. How about this case? You have four variables, 1 and 2 independent, 1 and 4 independent given 3, and 2 and 4 are independent given 3. What's the corresponding causal structure? Can you? Maybe I should write down. So we have 1 and 2 independent. Because of those relations, you know, oh, they are adjacent, they are adjacent, they are adjacent. Okay, and this is the V structure. So far, so good, right? And we can orient this one this way. Otherwise, we are going to have a fake V structure, this graph. Now the question is, do you think it's possible to have a confounder behind X3 and X4? By confounder, I mean a direct common cause, hidden direct common cause of 3 and 4. Do you think it's possible to have a confounder here? Yes or no? Now we are trying to go further. We want to say something about the confounder. Previously, we assumed the causal sufficiency, right? Is it possible to have a confounder over there?
Yes. Why not? I mean, it depends on our data, right? Like if the data doesn't say anything about the existence of a confounder, we cannot say that there is no confounder.
Yeah, you're right. In principle, from the data, we cannot check the assumption, right? We assume it's causal. Now, we don't assume that. We just have this set of independent relations, right? We don't assume causal sufficiency. Still, you can see it's not possible to have any confounder behind 3 and 4. It's not possible. Why? Because if there's a confounder, L here, then x1 and x4 cannot be independent given x3. Why? Because here, given x3, you have this open path. 1 and 4 will not be independent given 3.
Which path we can't see.
Oh, right? Here, x3 block, basically now if you have a confounder here, there are 2 paths between 1 and 4. This is one of them, from 1 to 3 to 4. This one is blocked by x3, right? This separation, this one is blocked. But this one, is open if you conditional x3, because x3 is a collider, right? Given the collider, there will be conditional independent. That's why if you see the independent between 1 and 4, you know, oh, there cannot be, and you know the direction here, then it's not possible to have any confounder behind 3 and 4, right? So you can see we can really, in many situations, we can really say something about whether we have confounders. This is another example. Here, again, we have independent between 1 and 3, 1 and 4, and between 2 and 3. What's the underlying structure? So you can see we have 1, 2, 1, 3 independent. Basically, they are independent. That's why this is a skeleton. Now you can see, oh, because this seems to be a base structure, I should use the original one. So here, this seems to be a base structure over here, and also here, 2, 3, and 4 seem to be a base structure. That means we have to orient the edge between 2 and 4 in both ways, right? Here you have a V structure, that's why you have the direction from 4 to 2. And over here, to the right, you also have a V structure. The orientation had to go from 2 to 4. Confliction, right? You can see a conflict here. That's why it's not possible to have a, to assume it's not possible to have, it's not possible that we don't have any confounder here. To explain that, you have to introduce a confounder L. That's why here we are sure there must be a confounder, at least a confounder, behind the 2 and 4. So you can see in the first case, we are sure that given enough data, we are sure there are no confounder behind some variables. And in this example, we are sure that there must be some confounder behind some variables. See that? That means, okay, we can really see something about whether we should have confounders in the system, right? That's very good. That's cool. In the first example, right? Only by analyzing only 4 variables, I can say something very strong. I can say definitely there are no confounder in the world relative to those 2 examples, two variables. This is so cool. Okay, here I just try to give intuition behind this. And if you allow confounders, basically, you just observe a set of the variables, right? Observe the set of variables, and the graph, the causal graph over the set of observed variables usually is not DAG anymore. As you can see from here, you cannot use the DAG to represent the relation between those variables. You have to introduce some latent variable. And actually, if you use, sometimes we use this to represent this relationship. 1, 2, double-headed arrow. This means there must be a confounder, double-headed arrow. Okay, so this motivates motivates the fast causal inference method proposed by Peter. Here, basically, you only have a set of variables, which is observable. Actually, it's just a subset of all variables that play a role in the underlying causal picture, which is the DEG. Now you want to infer something about the underlying causal information, causal picture from this observable set of random variables. That's all. And this method is called fast causal inference, although it's not really fast. Clearly, it cannot be very fast because you have to do a lot of independent tests. But with some tricks, this one, if the graph is pretty sparse, you can deal with system with more than 1,000 variables. Okay, I'm going to skip the detail. But you know that with FCI, we can deal with the confounders. We can even deal with selection bias. Although most of the time, the output of FCI is very conservative, in the sense that whenever it's possible to have a confounder, you see that. That means, oh, in most situations, I cannot really determine the causal direction. Why? Because whenever it can be explained by a confounder, the system will tell you that. Because the result is proven to be correct asymptotically, right? That's why sometimes it's not so informative. Okay, let me quickly talk about score-based methods for causal discovery. Any questions? By the way, if you use FCI, you can see the output is very different from that of PC. You use different ways to represent the output. You have this direct edge, and so on. Here, the circle just means that it could be a tail or head, arrowhead. Could be both of them. Okay. Score-based search. Previously, we just make use of independent relations in the data to discover, to recover information with the underlying causal graph. You can see some problems. Why? First of all, when you do the test, usually you do those tests independently or separately, right? You do this test and then you do that test. Most of those tests are actually related, right? If they are related, you should have a better way to combine, to do the test together, not separately, right? Each test only gives you a binary output, whether they are independent or not, right? That means here you are going to lose a lot of efficiency, statistical efficiency, right? Because you just ignore the dependency between different independent tests. So then alternatively, you can, I just want to find a single score function to measure the quality of different graphs relative to the given data. I just want to find the graph which fits the data the best, right? This is very intuitive. This is called score-based search. You want to come up with a score function, and then you have a search procedure, and then you have a graph, or set of graphs. So key issues here, I will go through this part very quickly. You have different scores. Basically, this is model selection problem. You want to fit, you want to explain the data. At the same time, you want the graph to be as simple as possible, right? Model selection problem. If you use BIC, you know, under some assumptions, BIC is consistent in model selection, right? So you can derive BIC from different perspectives, but basically here, we want to use a score that is consistent in model selection. You can use Bayesian scoring or non-Bayesian scoring. You can even use cross-validation. And the second problem is how to traverse the search space of the graph. You can deal with the space of DEX or the space of equivalence classes. It's much better. Why? Because in the linear Gaussian case, suppose we just have a linear Gaussian model. So all variables are just jointly Gaussian, and all causal relations are linear. In this case, you cannot determine the direction between two random variables, right? Because you just need to specify joint distribution. No matter the direction goes this way or this way, you are going to end up with the same joint distribution. That means from data, I cannot see the direction at all, right? You just have this. Now you can see, I don't want to go through all DEX. I just want to go through all those equivalent classes because I can only distinguish between different equivalent classes, not within the equivalent classes. Okay? And then the problem is how to do optimization. A very good method is called GS, gradient equivalent class. Yeah.
My question is, so is also finding the Markov equivalence class an NP-complete problem, or is that a polynomial time.
Or
Without any
again,
constraint.
it depends on the graph.
Yeah, no, without any constraint in general.
Without any, I don't think there are any result, precise result on that. Usually, you assume something about the graph, and then you can derive the complexity. Yeah, but GS is very. I would say, if the graph is pretty sparse, GS is very efficient. Basically, we can handle more than a million variables, more than millions of variables in the last year. So basically, you can even run it on your laptop. So it's very efficient. Let me quickly talk about the GES method. Search procedure is called greedy equivalence search. Some assumptions. The score equivalent means that the value of the score will be the same for different decks in the same equivalence class. And then it's locally consistent. It means that if you add an edge or remove an edge to introduce a correct conditional independence or dependent relationship, then the score will be higher. That's good. Locally consistent. You can use the score to change the to search, basically to do something like greedy search. And then the score is decomposable. For BIC, basically it means the total score is the sum of the individual scores. Each of the individual scores is associated with a particular variable and its parents. Okay, it's decomposable. BIC score clearly, in the linear Gaussian case, BIC score follows those properties. And then you can do the search. I'm going to skip the detail, but basically there are two steps. First, you want to add edges, and the second step is to remove edges. And this procedure has been shown to be correct asymptotically. That means if you have enough data, there's no local solution. You always end up with the optimal solution. That's very cool. With the greedy search procedure, you can end up with the global optimal. Here you can see how it works. Suppose this is the underlying two graph. Then first you will try to add some edges to explain the dependence. This one, and then after this you can see, oh, I should stop, because no further edges will change or will improve the score. This is the second example. Suppose this is the case, and suppose all those parameters are pretty small and similar. Now you can see, if you use GES, the first edge you are going to add is very likely to be this one. Why? Because the correlation between X and Y will be very high, because there are so many ways for them to be related, right? And that's why we have to use the second stage, which is to remove unnecessary edges. Okay, so you can see we can really solve the problem with GES. Any questions? If you are interested, you can refer to all those references in the recommended reading. It's very constant. The recommended reading is very short, and but all those problems are covered. Okay, now let's summarize what we just talked about. If you have reliable conditional independent test method, then you can use a constraint-based search. Usually it's difficult. Sometimes it's very slow, and maybe the power is limited if you really want to use a non-parametric test. That's a problem. And clearly this is the problem is ill-posed. Why? Because different causal structures can correspond to the same set of independent relation, as you can see from here. If you have this conditional independent relation between the variables, then you cannot distinguish between the three possible solutions. Then all of them will give you the same set of independent relations, right? Then why? It's because here we only make use of conditional independent relations. There's some information lost in the procedure. Okay? Why? Because usually when we say X causes Y, there's a process, there's a mechanism for X to influence Y. Now we don't make use of any information of the mechanism at all, right? So consider another example. If you have only two variables, clearly with this method, you have no idea. You can only say whether they are independent or not, right? Or further with the faithfulness assumption, you can say whether they are adjacent or not, but you have no idea about the causal direction, right? Okay, so now let's talk about the functional causal model-based approach. I will go through this part very, very fast. First, is it possible to do so? Let me introduce the concept of the definition of functional causal model first. Basically, you just represent the effect y as a function of x, a cause or causes, and some hidden variable, which is known as noise. You cannot observe it, right? But it's there. It's in the physical world, in the causal picture. It's hidden because it's not measurable. And in functional causal model, the noise is independent from x. Recall last time, maybe some of you can remember that last time when I said x causes y, I said the following thing. If x causes y without the confounder, then the generating process for x will be completely irrelevant to the process from x to y. The two things are completely separable. The two things are completely independent. So one way to see this is that here I have noise and they are independent. X is here, E is involved in the mapping from x to y. That's why x and E are independent. There are some other ways to instantiate this independence. This is very intuitive. This was known as modularity in the literature of causality a long time ago. And in the linear case, we have this functional causal model. Y is the linear function of x plus noise. Okay. Now the problem is whether we can determine the direction, causal direction between two variables, given only the statistical data. I think you still remember the definition of independent and conditional independence. But basically here you can see in the two cases, the two variables are uncorrelated, but they are clearly dependent. Over here, if I know the value of y, I can know the domain, or I can know the range of the other variable. That's why they are clearly dependent, but the correlation is 0. The correlation is 0 here, clearly they are dependent because x determines y. Okay, so here you can see different distributions. We have a Gaussian distribution. All of them have the same mean and variance. This is the Gaussian one, and this is Laplacian, this is uniform. Very different. Okay, here. X causes y because I generate y from x. This way, the noise E is independent from x. This is the scatter plot of x, y, and here, if you try to explain x to y, the relationship from x to y, you can see the noise after doing regression. The noise will be independent from x, and this is also the case for the reverse direction. If you try to explain x with y, that's very good. Gaussian case, symmetric. However, in the non-Gaussian cases, especially in this case, here x, the cause is uniform and the noise is uniform. If you regress y on x, the regression residual will be not only uncorrelated but also independent from x. However, for the reverse direction, you can see after doing regression, the residual will be just uncorrelated from x. By construction, whenever you do regression, the residual will be uncorrelated from the predictors. But clearly they are dependent, right? The same thing happened here. Here, the underlying variables are super Gaussian and Laplacian. X, y, this is a scatter plot. I do regression, then you can see the noise will be independent from x. But if I do regression from y to x, they are uncorrelated, the noise and y, uncorrelated, but they are clearly dependent. Because if I know the value of y, I know a lot of information about the other variable, right? So here you can see in the linear case, linear non-Gaussian case, usually we can say something about the causal direction between x and y. Why? Because for wrong causal direction, for wrong direction, you are going to have a dependence between the noise or the residual and the predictor. Okay? More generally, we have linear model, linear non-Gaussian cyclic model. Basically, just a generalization. Each variable is a linear function, linear combination of the direct causes or parents plus some independent noise. And you can see basically this set of equations, structural equations, correspond to this causal graph with those parameters. The problem is how to estimate this model, linear causal model. The theory basically, you can estimate this model. A solution is unique because of so-called independent component analysis, ICA. And later you can see we'll deal with general nonlinear settings. And you can see the linear Gaussian case is one of the very few cases where the causal direction is not identifiable. That means in almost all other situations, almost all the other situations, we can find the causal direction between random variables. Okay, this is the ICA. guess you know something about ICA. So you have the hidden generating process. You don't know anything about it. You apply linear transformation, or you adjust the parameters to make the output independent. And finally, the output will provide the estimator of the underlying independent signals. So W is the demix matrix, A is the underlying mixed matrix, which is hidden. Okay, so this is how ICA works. You can see finally you can make the outputs independent. And once you can do ICA, you know, oh, I can estimate the linear non-Gaussian acyclic causal model. Why? Because this is the causal model. In matrix form, we have this x equals bx plus e. B is our causal inference matrix. If one influences 2, then the corresponding entry of B, this entry will be the causal parameter. It's non-zero if x1 influences x2. Okay, if there's the edge, direct edge from x1 to x2. So this is called the causal inference matrix. All diagonal entries will be 0 for B. So you can see, oh, E is the linear transformation of X. E is the vector of independent error terms or noise terms. They are independent. However, they are just a linear transformation of X observed variables. That's very good. Similarly, for ICA, we have something. We apply linear transformation W to X, and the outputs as the components of Y are expected to be independent. Right? Here we want them to be independent. Here they are independent. That's why first you can apply ICA to recover W, and then you can analyze W to find the information of B. That's the idea. W corresponds to I minus B, right? That's why you can find the B. Once you find the B, you have the whole causal picture. Because Bij just gives you a causal parameter, causal coefficient from Xj to Xi. Okay, let me skip this. There are so many limitations of linear non-Gaussian acyclic causal model, although it's really cool. Why? Because it was proposed in 2005. I was surprised when I saw the paper. Basically, this is the first, to me, that was the first possible way to really see the causal direction between two random variables, right? Before that, it was not possible. So you have to deal with confounders, the measurement error, feedback, selection bias, and you have to deal with various nonlinearities. Let's have a very quick look at the causal models. This is a linear model, functional causal model, and this is called additive noise model, and this is called post-nonlinear model. Actually, it was proposed in 2006 because at that time I tried to analyze real data and I found that additive noise assumption does not hold. Most of your situation, we don't have independent additive noise. You have to apply some nonlinear function to make the noise independent. Okay. So with additive noise model, you can see, intuitively, you can see the identifiability. Why? Y is the nonlinear function of X plus noise. The noise is independent from X. That's why you always have the distribution for the noise, right? However, if you see the influence of, not influence, if you see the relationship from Y to X, if you try to explain X with Y, you can see as for different values of Y, the noise can have very different distributions, right? As you can see from here. That means, oh, if I try to explain X with Y, the noise cannot be independent from X. Again, you can see the asymmetry between X and Y. Okay? And more generally, we have post-nonlinear causal model because nonlinear sensor distortion is almost everywhere, especially in biology and the social sciences. And then we have this model, post-nonlinear model. And we try to establish the identifiability of the causal model. Meaning that we want to see whether the direction, causal direction, given by the model is unique. How can we determine the direction? Is because if the error or the noise is independent from the predictors or the hypothetical cause, we say it's a valid causal direction. Now, how can we deal with this problem? Here you can see some real data sets. You are given data points, and then you fit the model. You can see for the correct direction, the noise, estimated noise, is independent from the hypothetical cause. For the wrong direction, they are not independent. This is always the case. That's why you can determine the causal direction between even two random variables. And then in theory, identifiability. How can you prove this? Basically, you assume that for both directions, the noise can be independent from the predictor. Then you can find the implication of this assumption. And finally, you can see after solving some equations, you can see even for post-nonlinear model, which seems very complicated because you have sensitive distortion nonlinear function, right? There are only 5 situations where you cannot determine the direction, where for both directions you have independent noise. The first one is the linear Gaussian case, and basically all those 5 situations are very specific. You have to tune all those involved distributions and parameters nonlinear function in the system so that one of them can hold. That means, roughly speaking, generally, causal direction between 2 random variables is identifiable given their observations. Okay. So, extensions time series, you can deal with time series. Causality in time series is the traditional problem. And you can see by making use of functional causal models, especially linear non-Gaussian models, you can really find much finer causal relations from data, including instantaneous relations and causal discovery from subsampled aggregated data, or even from partially observed processes. Okay, and also you want to deal with non-stationary or heterogeneous data. Why? Because big data, right? We have so many data sets. If you combine the data set, clearly the data will be heterogeneous. They have different distributions. Here, I just want to say that causal discovery and non-stationarity of the data coupled. Why? Causal model tells us how to change the system. From non-stationary data, I can see the effect of the changes applied by nature or God, right? I just want to recover how it was changed. So we have some method to do so. You can really see the causal direction and causal picture, some result. And you want to deal with the measurement error. This is a very important problem because in most situations, we have measurement error in the system. And you want to find the underlying true causal picture over the noise-free variables, even if you have noisy observations. So we have some theory and method for that. And you want to deal with the selection bias. I will skip this part. And I should stop. Okay. Very tough too. I didn't give detail, but still. So let me pause this.